In this video, we will learn how we can apply multiple linear regression in order to apply a compensatory approach to making selection decisions. So an entire multi-tool selection system can use what's called a compensatory approach to inform selection decisions. Or a compensatory approach could be applied to one or more hurdles within a multiple hurdle system. A compensatory approach refers to the process of using applicant scores on multiple selection tools to predict who will have the highest scores on the criterion. In doing so, applicants can compensate for lower scores on one selection tool with higher scores on one or more other selection tools. Multiple linear regression model coefficients can then be used to weight each selection tool, thereby taking into consideration how much each selection tool contributes to predicting scores on the criterion. So as an example, let's imagine that we have the following selection tools: a cognitive ability test, abbreviated as CAT, a personality test, abbreviated as PT, and a structured interview, abbreviated as SI. Now our criterion or outcome variable of interest, let's imagine that that is some measure of job performance, which is abbreviated as JP. Now imagine that we've collected data, for example, as part of a concurrent validation design where we gave the selection tools to current job incumbents, and then at about the same time we measured their job performance, which is the criterion variable, and so now we have data on all of the models. Well, we can plug the data into a multiple linear regression model, and in doing so, we can estimate a multiple linear regression model. As a review, a multiple linear regression model means that the model has two or more predictor variables and a single criterion or outcome variable. If we had just one predictor variable and one criterion variable, then we would say that we have a simple linear regression model. So after estimating the multiple linear regression model, we get our model estimates for the coefficients. And as you'll see, we have the model intercept, which is the model constant. And typically we notate that by calling it B sub 0. And let's imagine in this example, the value for that intercept is 3.31 with an associated p-value equal to 0.06. In this case, this p-value is greater than the conventional alpha threshold cutoff value, and thus we would conclude that this intercept value is not statistically significantly different from 0. That being said, we're often not interested in the statistical significance of our model intercept value. Now, moving on to the more substantive values, we'll see that the regression coefficients associated with each one of our predictor variables and its relation with our outcome or criterion variable appears here on the arrows. And so starting with the cognitive ability test, you'll note that this notation for this regression coefficient is B sub 1 because it is the first predictor variable in our model. And the value of our regression coefficient, the estimate, is 1.32. The associated p-value is less than the conventional alpha threshold of 0.05. And so we would conclude that this regression coefficient of 1.32, representing the association between cognitive ability test scores and job performance scores, is statistically significantly different from 0 when statistically controlling for the other predictor variables, which are the selection tools in this model. Moving on, we can see the value B sub 2 for our regression coefficient associated with our personality test in relation to our job performance criterion variable, and we see that value is 0.45. It is also statistically significant. And then finally, we see B sub 3 here represents our regression coefficient for the relationship between our structured interview and our criterion of job performance, and that value is 0.61, and it is also statistically significantly different from 0 when statistically controlling for the other predictor variables in the model. So moving a step further, we can extract these coefficients, our B sub 1, our B sub 0, B sub 1, B sub 2, B sub 3, and construct a multiple linear regression equation. And so here you'll see that our criterion predicted, which is specifically job performance predicted, is equal to B sub 0, our model interceptor constant, plus B sub 1 times scores on our cognitive ability test, plus B sub 2 times scores on our personality test, plus b sub 3 times scores on our structured interview. Now, if we plug in the actual regression coefficients into this model, you'll see the following equation here. Now, let's imagine that sometime in the future, we have an applicant run through our selection system. They run through those 3 selection tools, and they generate scores on each of those selection tools. Now, this applicant, this hypothetical applicant, on the cognitive ability test, they earn a score of 11. On the personality test, they earn a score of 4. And on the structured interview, they earn a score of 7. Now, looking back at our multiple linear regression model, we can now plug these values here, these scores, from this future applicant's administration or taking of these selection tools. We can plug these into our regression equation to then predict a specific value for the criterion, which again is job performance in this instance. So here we plug the score of 11 on the cognitive ability test into the cognitive ability variable here, which again, here's the regression coefficient associated with the relationship between cognitive ability and our criterion of job performance. Next, we plug the value of 4 for the personality test into our equation here. And again, this 0.45 value represents the relationship between our personality test and our criterion of job performance. And then lastly, we plug a score of 7 for the structured interview into our equation here. And here 0.61 represents the association or relationship between the structured interview selection tool and our job performance criterion variable. Now when we put these all together, we can do some simple math here, and we can calculate that our job performance predicted, or in other words, our predicted criterion score for this particular applicant who had scores of 11, 4, and 7 on the cognitive ability test, personality test, and structured interview, respectively, their predicted job performance is 23.9. Now, if we take a step back and consider, well, there's often going to be multiple applicants that are going through our selection system, and therefore we're going to have multiple applicant scores on these selection tools, and thus we'll have multiple predicted criterion scores from the multiple linear regression model. So here we can see, here is that first applicant we just looked at. Let's call this applicant and say that it has a unique ID of AA1. That person's scores again were 11 on the cognitive ability test, 4 on the personality test, and 7 on the structured interview. When we plug these 3 values into our multiple linear regression equation, we got a predicted job performance of 23.9 in terms of the score. So this is the criterion score that's predicted for this person. This isn't actually observed data, rather this is a prediction here. So imagine that we have 6 other applicants as well, and here are their data, which are displayed here for each one of the selection tool variables, which are our predictors in the model, as well as our predicted criterion or job performance score here. Now, because this is a compensatory approach to informing selection decisions, an applicant's score on one selection tool, such as the cognitive ability test here, as you see 15 for applicant AA2, that can compensate for scores on other selection tools. So note here that this person scored the highest of all the applicants on the cognitive ability test, but scored the lowest on the personality test and the structured interview. Yet, if you look at their predicted job performance based on our multiple linear regression predictions, you'll see that they actually had the highest predicted criterion score, or in other words, highest predicted job performance out of all of the applicants. So again, because this is a compensatory approach, an applicant score on one selection tool can compensate for scores on the other selection tools. So again, here's that predicted criterion score there. Now, in terms of making selection decisions, it's common that we would then look at our column of predicted job performance, which is again our predicted criterion scores, and then we can sort these from highest to lowest, okay, as we do here. And so now you'll note that we've sorted this table by the predicted job performance scores here, and now we have a different order for applicant IDs, such that the applicant unique identifiers reflect from highest to lowest the predicted criterion scores. Okay, and so you can see our top applicant predicted is applicant AA2, next is AA1, next is AA4, AA3, and so on and so forth. So imagine that we have 3 vacant positions at our organization, and thus we wish to extend 3 job offers to fill those vacant positions. Using a compensatory approach to informing selection decisions, we could extend the job offers to these top 3 applicants based on their predicted criterion or predicted job performance scores. So we would extend those job offers potentially to applicant AA2, AA1, and AA4. Or if this were a multiple hurdle selection system, we would pass these top 3 applicants to the next hurdle. So again, these would be the 3 applicants that we would extend job offers to if we needed to fill 3 vacancies. And we made this decision, or this decision was informed by the fact that we plugged in their scores on our 3 selection tools that are part of our selection system. Their predicted criterion scores, or predicted job performance more specifically, were these values here, which we sorted by. So in this way, we were able to apply a compensatory approach based on a multiple linear regression model in order to inform the selection decisions here. So this wraps up the video on how we can apply multiple linear regression in order to make compensatory selection decisions.